Now after seeing the KVL and KCL, Kirchhoff's current law and Kirchhoff's voltage law, we can move on to other concept in current electricity. We'll start with what are the different measuring instruments, okay, which we encounter while measuring the current or the voltages. Now I will start with galvanometer. Now galvanometer is an electrical device which is generally used to measure small amount of currents flowing through it. Now basically galvanometer can be seen in variety of different forms, like it can be of moving magnet type or moving coil type. But generally in our applications wherein we need to determine the current and voltages, in this applications we'll be generally using in the labs, in the laboratories, we can generally see a moving coil type of galvanometer. Now in this type of moving coil galvanometer, we can see that the current which is the current which it detects, the current which is passing through the galvanometer, it causes some deflections in the galvanometer, and that deflection is proportional to the current which is flowing in the galvanometer. So we can see that there is a direct relationship between the current and the deflection in the galvanometer. Now this is why we can see that there is a linear scale in a moving coil galvanometer. Okay. Now we'll be now actually what we can see is that the amount of current, okay, which causes a deflection is which causes a large deflection is very small. Like what I mean is that even for a small change in the current, there would be a large deflection in the galvanometer. So if we'll be using directly a galvanometer to measure the current which is current flowing through the branch, it cannot measure very large amount of current. So if we want to measure a large amount of current which is passing through the circuit, we need to do some modifications. That is, if we want the galvanometer to be used as an ammeter, so we need to modify the circuit for the original primary circuit of the galvanometer in order to measure a large amount of current which is flowing across the branch. Similar is the case with voltmeter. Now we can also use the galvanometer as a voltmeter. A voltmeter is a device which is used to measure the potential difference between the 2 points. Okay, voltmeter is generally connected in parallel to the branch. Now same is the case, we can't directly measure, we can't directly use galvanometer to measure the potential drop, okay, because the internal resistance, the resistance which is offered by the galvanometer is very less, okay, it's not large enough, okay, it's not large enough to measure to be used as a voltmeter or an ammeter. Okay, so later we'll see what are the modifications to be done in order for the galvanometer, in order to for the galvanometer to be used as an ammeter or a voltmeter. Okay, now but first let us give the symbol for the galvanometer. Now galvanometer is generally given by this symbol G. Okay, now this G indicates the total internal resistance of the galvanometer. Okay, this is actually the resistance of the galvanometer which is given by the symbol G. Okay, so we'll be using this symbol. This symbol indicates that there is a galvanometer in the circuit, and this galvanometer by default it will be used to measure the current which is flowing through the branch. Okay, now our aim in the first point is to convert this galvanometer into an ammeter. Now in order to convert the galvanometer into ammeter, okay, first we need to see what is an ammeter. Okay, so if we'll consider an ammeter, now basically an ammeter is a device which is used to measure the current which is flowing through the branch. Suppose we consider an ammeter, okay, branch, okay, through which some current I is flowing. Now in order to determine, in order to measure the value of I, we need to connect an ammeter in series with the branch. Okay, in series, if so if we can see from here is that if the ammeter is connected in series with the branch, with this branch, okay, the same amount of current will flow through this ammeter. But what happens is that if we'll be using an ammeter, the ammeter itself will be having some internal resistance, and that internal resistance, okay, that internal resistance is such that it will draw some amount of current. Okay, the internal resistance is basically parallel to this. Okay, now this internal resistance, okay, will draw some amount of the current. Okay, so in short what we can say is that this ammeter can't measure the full current I which is flowing across this branch. Okay, there would be some, it will be measuring a current which is lesser than the value I. Okay, now this is how an ammeter works. Okay, wherein we have seen that because of the internal resistance it can't measure the entire amount of current. Okay, now here in this part, what we have to do is we have to use this galvanometer, and we have to convert this galvanometer into an ammeter. Okay. Now if we'll see that we have just seen that in order to measure the current, we need to connect the ammeter in the series. Now if we are connecting something in series, then the internal resistance for that thing is in parallel to the device. Now if suppose if we are seeing a galvanometer, okay, this is the galvanometer. Okay, this galvanometer is showing a full scale deflection of IG. Now what does this full scale deflection indicates is that for a current IG flowing across the galvanometer, the deflection in the galvanometer would be maximum. Okay, so this is the original full scale deflection current IG. Now what we have to do is we have to increase the range of the current which can be measured by the galvanometer. That is, we have to use this galvanometer as an ammeter. So in order to convert the galvanometer into an ammeter, we'll be connecting a shunt resistance across the galvanometer. Okay, let us indicate the shunt resistance by a letter S. Now shunt indicates a parallel resistance, okay, which is connected across the galvanometer. Now our aim is to measure a larger amount of current. Suppose that larger amount of current is I. Okay, so we need to measure a current I, okay, which is a value which is required to be determined. Now as we can see that IG is the deflection, is a full scale deflection current which will go through the galvanometer. Okay, so if we'll apply KCL at this node, we can see that the remaining amount of current, as per KCL we know that the total incoming current must be equal to the outgoing current. So in this branch we'll be getting a current of I minus IG. Okay, so this is the current which would be passing through the branch containing the resistance, shunt resistance S. Now if we can see from here is that if we want that the galvanometer must detect the entire amount of current, so in order to detect the in order for the galvanometer to detect the entire current, the current which is flowing through the shunt resistance should be minimum. And how this can be achieved is by connecting a very large resistance. Okay, a very large resistance, if we'll connect across it, we can see that a very small amount of current will pass through this shunt resistance. Okay, so basically what we can observe from here is that this galvanometer has a shunt resistance, okay, and the current which is passing through this shunt resistance is I minus IG. Now in order to determine the value of S, the shunt resistance, to be connected across the galvanometer, we can see that since both of them are connected in parallel, the potential drop across these points would be same. So the potential drop across the galvanometer is, as per Ohm's law, it is current multiplied by the resistance. So we will be having IG times G. This is the potential drop across the galvanometer, and the same potential drop could be seen across the shunt resistance since both of them are connected in parallel. Okay, now the potential drop across the shunt capacitance, the shunt resistance, by using Ohm's law, this would be I minus IG times the value of the shunt resistance. So if we'll solve for S, we will get the value of S as so this is the value of the shunt resistance which has to be connected in parallel across the galvanometer in order to increase the range of the galvanometer so that it can detect a current of I amperes. Okay, later on